Hello, I hope you're all enjoying this very sunny bank holiday weekend. The other day I was watching someone stream on Twitch how they were performance tuning a application written in .NET Core, and their goal was to reduce the amount of memory used by the application. And I thought it might be quite useful just to put together a short video showing the steps you can go through to do this. So coincidentally I was given some code at work the other day which needed rewriting, and I thought that would be a good piece of code to use as an example today. So this is a piece of code here. So it takes in a string, it splits it based on a full stop. If it had contained a full stop originally, it returns the final part of our array, otherwise it returned the original string. In other words, it returns everything after the final stop in the string. So I found that quite hard to read, and so I needed to rewrite it. And when you're rewriting code, there's sort of three things you're interested in. The code has to continue to do what it did before, so it has to be correct. You also want it to be readable, so you can maintain it in the future, and you can understand it when you read it as well. And finally, it has to have the correct performance for your sort of needs. So by that I mean, if your code's only going to be called once, it doesn't really matter whether it takes a tenth of a second or a hundredth of a second to run. However, if you're going to call it hundreds or thousands of times every second in a loop, then performance could be a bit more important. So, with the first thing in mind, making sure the code continues to do the right thing, we need to write some unit tests. So, I tend to use XUnit for my tests, so I'm going to use that. Normally, I would create a new project, a new XUnit project, which would give you the NuGet packages automatically. But because I also want to do some performance tuning, I've created a basic console application. So that means we need to add our NuGet packages first of all. So the ones I'm going to install is XUnit and also Fluent Assertions. So before we can write our test, we need to move our code into a method where we can test it. So I'm going to create a new class called services. And in here I'm going to have one method for each implementation of our code. So every time I change our code, I'm going to create a new method in this class. So it's going to return a string. This one I'm looking for the original version. And now I can write our tests again. So again, I'm going to create a new class. This time I'll call it tests. And I'm going to have one test per implementation again. So in XUnit, you can either label up your test as a fact, in which case it's going to be called once without any input, or you can say it's a theory, in which case you can provide data to it as you run your tests. So I'm going to use a theory, and I'm going to give it a couple of different strings to test with. So the first string will just contain the word 1, and the result from that we'd expect would be the word 1, because it's got no dots in it, so the whole string's returned. Our second test will be 1.2, in which case it contains a dot, so everything after that dot's going to be returned, so that should be 2. And our final test will be 1.2.3, and again we only want the last thing to be returned, which will be the 3. So that's going to take in our input and also our expected result. And tests normally return void, so that's that. So our test is quite straightforward now. We create an instance of our service. We then call our method to get the actual result. So that takes our input. And then finally we say our input should be our expected result using Fluent Assertions. Our actual result should be our expected result. Okay, so and then we don't need this code up here anymore, and we can run our test. Okay, so the first problem is we've actually hit an error and we can't actually compile our code. And we got this error here saying our program's got more than one entry point defined. So This means that it thinks it's got more than one method called main, which is quite strange because we've only written one ourselves. So what's happening here is, as part of the test framework, is it's automatically trying to create a method called main, because it doesn't normally get ran within a console application. Fortunately, this is quite easy to fix. We can add a setting to our project file which just tells the test framework not to generate a main method. So we have to add in that line here, and now we should be able to run our tests. Okay, and our tests have gone green, which is good. So before we can do any other implementations, we also want to look at the performance of the original method. So the way we can do that is we can store another NuGet package, which is a program called benchmark.net, and we can then create another class which is going to contain our benchmark tests. So as before, we're going to have one method per thing we're going to test. And so we will create our class. So we don't really care if the method returns the right value at this point, because we've tested that elsewhere. All we want to do is just test how long it takes to call the method. And there's clearly two different code paths to our application, when we've got a dot and when we don't have a dot, so we can test both cases. So we have our simple case and with dot case. And then as part of the test, we don't really want to test creating a service, we just want to test calling our methods. So we can create our service in the constructor. And a bit like with the XUnit tests, you have to give the methods containing your tests an attribute, so the test runner knows it's a test method. And this time we say it's a benchmark. And what you can also do is label up the original version of your code and say that this is the baseline which we're going to compare all the other results against. So by default, benchmark.net records the time it takes for your application to run, but we're also interested in the memory usage. So if you want to capture memory as well, you need to add an attribute to your test class, which is memory diagnoser. And the final step is you have to actually, in your console main, actually run your benchmark tests. So we can use the benchmark runner to do that. And that's a generic method which takes in the class containing your benchmark tests. So just to summarise, so when the program starts up, it's going to run any tests in benchmark tests class down here, and these are the ones marked up with the benchmark. And this is our original version of our code, which is going to use as the baseline, and we're also going to capture information about the memory usage. A couple of things is, when you run the tests, you should always run them in release mode, and normally you shouldn't run them within Visual Studio either. You should compile your code and run it directly within the command prompt or Windows Explorer. For the sake of this video, I'm just going to run it from within Visual Studio, however. So this it runs the code quite a few times to get a realistic sort of result, so there's no fluctuations depending on what your computer's doing and so on. So it takes a few seconds before it's run it that many times. So in each test run you can see it's going to run it this number of times. So this number is quite high because our code's quite simple, so it can run it lots of times. So we should get a fairly accurate figure out. There's also quite a lot of other settings and things you can do with the benchmark.net program, so if you're interested in that, you can look at their website. Okay, so that's completed, and it generates a graph or a table, and this table is going to have one row for each of our methods for testing. So at the moment we've just got one. So the numbers that we're interested in at the moment is how long it takes and how much memory is allocating, so how many objects it's creating. And that's how often the garbage collector runs as well. So our method's quite simple, so these numbers are low, but we can still see them change as we change the implementation of our method. Okay. So the first thing is it's a bit of a strange method in that we do half of this work using link, so the any statement, and then we use direct array access to here. So a different approach could be, so we'll call this one full link. So instead of doing this, that's really just the same as path.last. And then we can copy our test for that. So in the subsequent tests, they're no longer the baseline, so we can remove that property from our attribute. I probably want to put that one first. So that's one approach, so we can run our test just to make sure that still does the same thing. Okay. However, I still don't think that's particularly readable, and so maybe an alternative would be to not use any link at all. So here we're really saying is we're checking that we can it contains a dot. So in other words, our array has got more than one entry in it. So we can just say if path.length is more than one, then return the final part, otherwise return the entire string. So we can add some tests around that as well. So one of the things about if you're going to be copying tests like this is you have to be very careful to make sure you actually use the new implementation each time. If I forgot to replace this word here and ran the test, it would just still be using the old version of the code. You need to take care when you're doing that. So normally in test-driven development, you'd have a failing test first to avoid that sort of problem. Okay. So then the next thing is, if you look at this code, is this check actually important? Because if the string doesn't contain a dot, then we end up with an array with just one element in it anyway, and so if you return the final element, that is the entire string. So you don't actually need that check anyway. So we could always return the final element. So we just check that's all running okay so far. Good. And then for the next implementation is maybe this is still more complicated, because all we really want to say is we want to return everything after the final full stop, if there is a final full stop. So we can find the final full stop by using the index of method. So last index of. So we can say, so we find the last full stop in the string. That's a character. If there isn't one, it's going to return a negative value, in which case we just return the entire string. Otherwise, we return everything from the full stop onwards, and we can use the new range keyword for that. So, if it doesn't contain a full stop, we return the entire string. If it does contain a full stop, we return everything after the full stop to the end of the string. And we can prove ourselves that still works. Implement that. And if this works, we can then check the performance to see how our different implementations have changed the performance. So we're still in release node, so I'll run that now. And this is going to take a few seconds to run, so I'm going to pause the video and resume it once it's complete. Hello, it's finished the running the benchmarks out, and this is our table of results. You can see we now have one row for each method. So that was our original one. And when we went for the full link solution, so that was using parts.last, you can see it actually runs slightly slower, but uses the same amount of memory. When we remove link, and no longer uses the any keyword or any link at all, you can see it actually runs a lot quicker. Looks like it's twice the speed, and also uses less memory. When we simplified our logic by not having the if statement, so no check, it seems to run slightly slower, but those figures are pretty similar anyway, and again no memory, so there's not too much difference between those two. When we use last index of, however, instead of using this string split, so we're not creating the array anymore, you can see that runs much quicker and also uses a lot less memory. So this is hardly any memory at all. So this memory here is coming from here, because at this point we're creating a new string which is a subset of the final string. So if you want to reduce this figure further, we need to avoid creating this string, and the way we can do that is we can use something called a span. So you think of a span as being a window onto an existing string, but only so it's like an existing string, but it says we're only interested in the sort of third character onwards, and we're only interested in the length of, say, 4 or 5 characters. So it's a window you can position of any size over the top of the string. So the way we can do that is we'll create a new method which we will call span. And instead of returning a string, we can return a read-only span of characters. Because if you think about it, a string is just an array of characters. And as you can see, it's done an implicit conversion from the string to a read-only span. So we can write a test. Span. So the problem here, and this is the disadvantage of returning a span from your method, is you're now changing sort of the interface to your method. So whereas before we were returning a string, the calling code now has to handle a span being returned instead. So in this case, we can just convert our span back to a string. So the allocation is still happening, but it's happening outside of our test. So our test will pass. So it only makes sense to return a span if the code calling your method can actually handle a span. If all you're going to do is convert it to a string straight away, that you're not going to get any benefit. Okay, so that's doing the right thing. However, there is actually a bug in our code. If we go back to implementation. So what's happening here is it's taking the string and it's doing an implicit conversion to a span before it returns. And here it takes our string, creates a new string of a shorter length, and then does the implicit conversion to the span. So what's happening is it's still actually generating our string and it's still doing an allocation. So what we need to do instead is turn our string into a span first, using the add span. So this won't cause an allocation, and then you can return a slice of that span again without generating using an allocation, so you're not putting any memory to create an object. So as before, we can add our tests in. And we also need a couple of benchmarks to prove it's doing what we expect it to do. Span 2. So, as always, you should run your test just to make sure you haven't broken your code and it's still got the same behaviour as before. So, make sure our code's built. So this time I will run the actual compiled version, which is console app 11. And again, I'm going to stop the video and resume it once it's finished running. Last time it took about, I think, 2 to 3 minutes to run all the tests, so it'll be about the same again. Right, that's now completed, and you can see that if we look in our bin folder, bin release folder, there's a folder called benchmark.net artifacts, and in here, every time the benchmark test run, it generates a log file. We look at the most recent one. Let's scroll to the bottom. You can see our table of results we were seeing before, with the new entries for span and span 2. And as you can see, our first version of span, where we had that bug where we were allocating the new string before generating the span, didn't make any difference at all. It still allocated 32 bytes. However, when we fix our span method to work correctly, you can see we're no longer doing any allocations. So it means the garbage collector never has any work to do, and actually also it's a faster piece of code to run. So the important thing here is when you're doing performance tuning is you should only change one thing at a time, and then make sure you always measure when you make a change, because our gut instinct was switching to using a span would be better in terms of memory, but it wasn't until we tested it that we realised that actually it's not. And likewise, by removing the if statement, we thought maybe that would give us a reasonable improvement in performance, but as you see here, it makes hardly any difference. So if we look at our implementations here, we'll just go down them. So that was our original one, which I found was quite hard to read and understand, and also performance wasn't particularly good. Going for a full link solution makes the code a bit more consistent, but uses more memory, but runs slower. Going without link actually makes the code a bit more readable, I think. We can remove the check, again, makes the code a bit more readable because it wasn't actually doing anything, that check. Last index of, I'd argue, is probably actually more readable than these approaches, and uses a lot less memory and runs quicker. That span one doesn't work. And finally, span 2, if the calling code can process a span being returned, then this is a good alternative solution. But it is more complicated, and so if the performance isn't important and the calling code can't use a span, then maybe you're better off just sticking with the last index of. Hopefully you found some of those techniques useful and you'll be able to use them in your own applications. Thank you for watching.